This is the North Sea. If we were to place wave energy converters over a 150-kilometre stretch of the Danish sector of the North Sea, and if these converters could achieve an average efficiency level of 25%, annual net energy production would amount to 5 terawatt-hours. This corresponds to 15% of Denmark's electricity consumption. We did it with wind power. Can we do it again with wave energy? In November-December 2000, 22 megawatt wind turbines were installed in the sea not far from Copenhagen harbour. While wind power is well on its way to conquering the sea, wave energy is still at a development stage. Because of our shallow water coastlines with limited wave heights close to the shore, we in Denmark must venture out into open sea with our wave energy converters. And so far no one has developed anything convincing out there. With its wave energy program, the Danish Energy Agency stimulates development of both recognized and new ideas for wave energy converters. Support is given to both simple function tests using scale models, involving a number of basic concepts concerning converter principles, and, in a phase 2, to advanced tests and optimization of converter types, which are further along in the development process. Both inventors and researchers, companies and private individuals can take part. There's a need for broad participation, including investors. The experiments with models follow standards set down by the Wave Energy Program. In a converter's initial development phase, function, survival and estimates of efficiency levels are focused upon. Later, further development and optimization take place. From 1998 to 2004, the program has up to 80 million Danish kroner at its disposal. This is Swan DK3, one of more than 40 different concepts which have received support. It's a further development of Japanese Yushi Masuda's concept backward bent duct buoy. Swan DK3 was built using the principle of oscillating water columns, a principle which has been tested previously on coasts around the United Kingdom. The column of water is enclosed in a bend channel system, which is open at the end facing away from the waves and closed at the vertical end, which is above wave level. The construction allows the water column within the channel to oscillate in resonance with the wave period. This forces the air above the water column back and forth through 2 air turbines which drive the generators. The Swan DK3 model has been tested by DHI Water and Environment with promising results. Wave Dragon is an overtopping wave energy converter which will not be placed along a coast, but anchored in the open sea. The waves are caught between long floating concrete arms and guided up into a reservoir. The water in the reservoir runs back to the sea through specially developed Kaplan turbines. The development of Wave Dragon is conducted as a joint project between 12 different corporations and institutions in Europe, amongst them Eltra, Cork University in Ireland and Aalborg University, Denmark. With its hydraulic facilities and expertise, Aalborg University is one of the centres within the Danish Wave Energy Program. Wave Dragon is tested here at the university using a model on a scale of 1 to 50. Munich, Germany, October 2000. A development study on power conversion is carried out in connection with the Wave Dragon project. One of the technical challenges of the overtopping converter is the conversion of the low head water flow and the control strategy necessary to obtain a smooth electrical output with high efficiency. The Munich project is supported by the Wave Energy Programme and the European Commission. In Denmark, development under the management of the Wave Energy Programme aimed at improving power conversion systems is about to be initiated. The wave plane is another floating overtopping converter. The waves are caught between guide vanes and channeled into a rotating flow in horizontal pipes on each side of the converter. Ongoing tests will reveal how much energy can be captured and converted by turbines placed in the outlet of the pipes. The wave plane is tested here at the Danish Maritime Institute. Power pyramid is an example of a new idea that tries to combine principal elements of the two foregoing converters, the Wave Dragon and the Wave Plane, by introducing several water reservoirs in different heights above each other, leading to a central water turbine. An initial test has confirmed that energy from a wider range of heights can be captured more efficiently. The point absorber, the third category of wave converter, has been a pioneer project in Denmark for many years. With this concept, which has the name point absorber today, the entire power conversion system has been moved up to the float, where in the earlier version it was on the seabed. The model is on a scale of 1 to 10. Point absorber's float is attached by a rope to an anchor on the seabed. The effect of the movement of the waves on the float is transferred to a pump inside the float. By means of a hydraulic system, the pump drives a hydraulic motor, which in turn drives a generator. Oil-gas accumulators are built into the hydraulic system. This creates a relatively smooth output from the pulsing energy of the waves. Wave plunger is a point absorber with an asymmetric float which runs up and down a sloping lattice tower. The lattice tower has to be attached to an anchor on the seabed and turns with the waves when they change direction. The reverse side of the float is flat and doesn't create waves in a leeward direction. The inventor therefore expects that the system can achieve a high level of efficiency. The model is on a scale of 1 to 25, and the first test has demonstrated a relatively high conversion efficiency. The wave pump combines a float and a seawater pump attached to an anchor on the seabed. Several pumps can be connected to a central water turbine. Poseidon is a complex point absorber which transforms the movement of the waves into hydraulic pressure. The many floats activate pumps relative to the construction's pipes, which are static. Water is pumped into the pipes, leading to a central turbine at the rear end of the device. The converter, with its large dimensions, will be anchored to a special, patented anchor buoy. A wave machine is being set up at an outdoor test site, known amongst the inventors as the playpen. The test site is established to facilitate initial testing of the models and converters supported by the Wave Energy Programme. It's located in a fjord, Nissum-Bredning, close to the North Sea. The waves are smaller than in the North Sea and therefore well suited to model experiments. The site is operated by the Forker Centre for Renewable Energy, in cooperation with the Association for Promotion of Wave Energy, the Inventors Association. The use of the test site, including technical and testing supervision from the Forker Centre, is free of charge for the inventors. system is also a point absorber. It comprises a number of floats which are attached to cylinder pumps inside a long pipe. With the effect of the waves, the pumps create excess pressure in the pipe, forcing water out through a turbine at one end of the pipe. The wave boat was previously tested at a harbour. It's a double point absorber. The energy exchange takes place between the central floating converter and the two floats. This is now to undergo more extensive tests at the test site. The fourth, and so far last of the wave energy converter archetypes, is the wave turbine system. The wave turbine is a floating water turbine. The vanes are situated just under the waves and rotate horizontally around a vertical axle. As with wind turbines, the vanes are made of fiberglass. The turbine generator is placed over the vanes. Two turbines are attached to one another and rotate in opposite directions in order to avoid torque in the moorings. The two rotating discs below inhibit vertical movement of the water turbines. A simplified model of the wave turbine is tested here at Aalborg University. The wave rotor combines vertical and horizontal vanes. The horizontal vanes are driven by the rising and falling movement of the waves. The vertical vanes utilize the horizontal movement in the waves. The turbine must be permanently fixed on the sea floor. This set of propellers is part of the converter called the wave energy module. The module is made up of a float and two sets of propellers under the float. When the float rises and falls with the waves, the variable pitch propellers rotate in the same direction, and via an axle they drive the two electricity generators situated inside the float. There is no doubt that large-scale utilization of renewable energy sources is one of the key elements in a global strategy for a cleaner and more sustainable energy future. But whether or not wave energy converters will in time break through technically and commercially ultimately depends on whether the price of wave-generated electricity can be reduced to a level where it can compete with other electricity-producing renewable energy technologies, including offshore wind turbines. Until now, 10 converter types have been through the initial tests and measurements for efficiency. The best show an average efficiency level of about 10%. In order to compare the projects in a systematic fashion, the relationship between material costs and annual energy production is calculated based on a standard set of criteria. At a price for electricity of less than 10 Danish kroner per kilowatt hour, the best of the tested converters would recoup their own material costs in 1 year. Costs for installation, mooring, electrical transmission and maintenance are not included in these calculations. In the wave energy program, quantitative comparisons are made of all the supported converter types with regard to factors such as economy, efficiency, survival and complexity. After 2.5 years of program work, there's still a long way to an efficiency level of 25%, but there is a significant potential for improvements in design and power takeoff systems. The hope is that out of the program, 1 or 2 converter types will stand out as clear candidates for a more concentrated and far more costly long-term development process.